All right. Morning, everybody. Don't know why there's a meeting room or a waiting room. That's the correct terminology for it. But we'll figure it out as we go. All right, so the quiz got moved till the end of class. So that way, if anybody has extra time, that it won't be interfering with them learning or anything like that as far as that goes. All right, so at, let's see, 11 o'clock, the quiz will open up. We'll end about 2 minutes before, so we'll get all ready. All right, so help me watch the time, and we'll go from there. All right. It's 10 questions. Shouldn't take you too long. All right. I don't think I've seen anybody even use the full extra time either in the past 2 times I've given this quiz. So that'll give you some hope as to how easy it is. All right. Pull up the PowerPoint and we'll begin. Oh, and I want to do one last thing with valves. All right. Want to make sure this hits home. Where is it? That's it. Now, question, is this blurry still, or is this good now?
That's good. That's good.
It's better than what it was? Or do you still prefer the share screen? Which one's better?
I kind of like the share screen. It's also bigger. The share screen one's bigger.
If you go to speaker view, all right, so we'll do that. Let's see. Do that. Is that better?
Yeah.
Yes.
Yeah, a lot better.
Yep.
All right, sweet. Then I'll stick with that. I was trying to figure if I could fix something. All right, so with this, the air-controlled pilot valve, all right? I was talking to someone yesterday with office hours, all right? What I want to hit home on this is just basically a small analog computer. It's a mechanical computer, all right? Over here, we are measuring something, whether it's the steam pressure or temperature or what have you, all right? We have an air supply coming in, and that exact same air supply is coming out, but just at a different pressure, all right? So this air control pilot valve has like a ratio in it, all right? So if you wanted to, and I gave this analogy yesterday to this person, if you had a recipe to make 100 cookies, right? That's what you had for. But you wanted to go from anywhere from 1 to 100. All right. If I gave you the recipe for 100 and I asked you to make 50 and only 50 with the ingredients given, would you be able to do it using some simple math? Because you know the ratio to 100, you'd be able to figure it out to 50, right?
Yes.
Now, well, that's all this is doing. You're just basically bringing the number down. You have what you have. What you're coming in at is what you're measuring. It's what you want. So if you want to make those 50 cookies is what is being measured, all right? Your ingredients is your air supply and how much of those ingredients are coming out, because you're not going to turn the piece of paper that writes 50 down for the order into this. You're going to take your ingredients, which is your air supply, and turn it into whatever it is you want. All right. So keep in mind, this controlled pressure is not going to end up going out into the operating air pressure. All right. Only the air supply, after going through a ratio, will it go out to the operating air pressure. All right. It's all based on what's being measured all the way down here. All right. It's the same thing. If you don't like the cookie one, then you can go for the kilometers per hour that you want to go to meters per second. All right. You have kilometers per hour over here. And what's going to be spitting out is going to be meters per second. All right. It's all it is just a ratio. All right. But this extra line over here, this air supply line over here, is what's actually coming out and going into the actual valve. All right. So there's just some confusion on that. All right, let's go into piping. Oh, and there is some people still haven't signed the paperwork. I don't know what your deal is, but I didn't make it worth any points, but I might make it worth points. Get it done by the end of the day today, or you start losing points. You have to do it. It's not an option. All right. So going into piping. All right. So first of all, we're going to do some nomenclature. So piping refers to any assembly of pipes, tubes, valves, and fittings that form all or part of a system for the conveyance of fluids. A pipe refers to a non-flexible fluid conductor designated by the diameter and wall thickness, either strength or schedule. All right. Tubing can be, and usually is, bent at installation. It's more flexible than pipe and is designated by the nominal outside diameter and the wall thickness. Fittings are devices employed to join sections of piping, tubing, or hose in a piping system. All right. So nominal pipe size, or NPS, is approximate inside diameter of a standard pipe, Schedule 40. All right, so here's an example. This is a 3-inch standard pipe. All right. So its outer diameter is 3.5 inches. Its inner diameter is roughly 3. All right. So its wall thickness is 0.216. All right. Now, if we have a Schedule 80, remember this one is going to be, this one right here is scheduled 40. All right. So Schedule 80, you can see its wall thickness has increased, but the outer diameter has not increased in size. We have decreased the actual size of the inner diameter. All right. And then we have a 3-inch Schedule 160. Again, we have not increased the size of our outer diameter. We have only decreased our inner diameter to get a bigger wall thickness. All right. So why is it important to know schedule and all that other stuff? What's the whole point?
So we use the proper piping for the application?
Exactly. So you guys are going to be third engineers. That's what you're training for, right? So when you get to that, and then some of you are third mates, but still, you were going to be the ones ordering supplies. The chief engineer is only going to be sitting there clicking on the computer approve. All right. He's not going to be looking too in depth. If you need a certain amount of feet of 3-inch scheduled 160 pipe, and you order just standard Schedule 40, you're going to have a really pissed off chief engineer because it's a waste of money. And also, now whatever project you're working on is going to take longer because now you have to wait for the next shipment. You can't just run to the store. It might be months, it might be weeks, it might be days, or anything in between. It depends on where you are. All right. I worked on a dredge boat for a while. We had 3-inch thick walls. It was the actual physical wall of the pipe was 3 inches. All right. This pipe could be anywhere from 6 feet in diameter to about 3 feet in diameter. All right. The actual steel that was made out of was armor plated because every single day we were sandblasting our equipment because our job was dredging. Our job was sand. All right. We picked up sand in one spot and we put it in another. The only way to do that, it was with basically giant vacuum pumps that we used. The whole ship was a vacuum cleaner. All right. So we were constantly sandblasting our equipment. Within 6 months of putting in that 3-inch walled piping, we had to start doing what was called UT scans. All right. And that actual scanning was basically, they sent a little bit of a wave in and it would tell you the actual wall thickness. All right. That 3-inch armor plated steel that we had was down to 1/4 of an inch in some places after 6 months of use. If you ordered Schedule 40 piping, I think my chief engineer would have just tossed me off the boat in multiple pieces for replacing 3-inch wall thickness. All right. The reason we had to start doing that was because we started busting holes through our piping. All right. Again, 6 months, we lost 3 inches of wall thickness due to sandblasting. Just moving sand from one spot of the ship to the other. So, nominal pipe size, or NPS, for pipes with an outer diameter of greater than or equal to 12 inches is going to be the outside diameter. All right. So if we have a 16-inch standard or Schedule 30, all right, its outer diameter is 16 inches. Its inner diameter is 15.25 with a wall thickness of 0.375. All right. And you can see the rest of these go from there. Again, the 16-inch outside diameter does not change. Tube size. Outside diameter in inches or 16ths. All right. So number 12 tube has an outside diameter of 3/4 of an inch. A number 16 has an outside diameter of 1 inch. All right. Wall thicknesses is as a decimal, 0.065, or in the BWG wire gauge. All right. Same thing as wire. All right. So an 18 gauge is a thinner wall and a 14 gauge is a thicker wall. All right. That's why if you have like a 12 gauge wire, it's going to be a lot thicker of a wire than if you had something that was 18, it's going to be a lot smaller gauge. All right. Copper tubing falls into its own category, even though it's sort of considered tubing. All right. It's just designated by different parameters because you can use fittings with it and you can also bend it. All right. So it falls into its own sort of category. So you have its piping size, which is done by its nominal size. All right. So it's the actual outside diameter. So a 1-inch copper tube has an outer diameter of 1.125, or a 3/4 inch piece of tubing, copper tubing, or you have a 1/2 inch copper tubing. It's just a little bit bigger than what it is if you measure it. All right. And then it's designated by wall thickness. So you have types. So it's like K, L, M, with K being the most robust. All right. Basically saying that K has the thickest wall. All right. Also, the type of material, even though it's copper, it can take a little bit more of a hit. All right. So I told this story to the other class because they got a little bit farther ahead of you guys, but I just replaced the water line to a hose spigot in my garage. All right. I had to use K-type, 1/2 inch K-type piping because it's in the garage, it's exposed. All right. One, it'll have a higher chance of not freezing and busting a pipe open if we forget to turn the water off. All right, because as a thicker wall, it can stand up to a little bit more pressure. And then 2, it's a garage. We hang a lot of stuff in there. So a lot of that stuff can bang into it and dent it and cause problems and weakness. So we had to go with the type K. All right. So knowing that is important as well. All right. So how do you connect piping? All right. So you can weld it. All right. This is called the butt weld. You'll use what is called a V-groove. So these grooves are already on the piping itself. All right, so if you order a piece of pipe, it will come with this V-groove already in it. All right. Sometimes you'll have to grind it yourself, whether if you decide to, cut a piece of pipe, you'll have to V-groove yourself out. All right. It's just a 45-degree angle about, and all it's designated is that way you can stick weld in there and you can actually get a really good weld. If you just surface weld, you're not going to really be getting a whole lot of material there. All right. That gives you a greater surface area. That's called a backing ring. It goes inside. I have never used one of these in my life. I've never seen a welder use one of these in my life. All right. So fill it with weld. It's not a welding class, but this is a way to secure 2 pieces of pipe together utilizing that V-groove. All right. Now, this is a little bit more typical that you'll see with fittings. Not a lot of places really stock these as much. This was definitely the older style. All right. This has more of like a coupling outside. All right. It's going to be a larger diameter than the pipe itself, and the pipe goes into it. All right. You'll never really see it in the opposite direction, because if you do, then you're going to be losing material on the inside of your pipe, and then you're going to be slowing down whatever fluid is going through. Plus, if you have just a straight wall there, you're going to have eventual wear. It'll erode it. All right. Now, right here, that white line, is that something that was done on purpose, or is that just bad animation?
I assume it's on purpose.
It's on purpose, but why?
Don't you stick something in there to like help keep it watertight or something?
Gasketing.
It's not going to have a gasket. Remember, we're going to be welding here. What happens if this is a steam pipe and steam is going this way? You're turning on the steam plant for the first time.
You have to allow it to like go out.
Expansion.
It's going to be expansion. All right. Remember, these are 3D. We're just basically cutting a pipe in half. All right. So you're not going to, we wanted the conveyance of fluid. We don't want anything that's in here to come out of the pipe. All right. So it's expansion. It's just that little bit of room for expansion. All right. You put it all the way in, and then you just pull it out about a 1/16 of an inch. Nothing too great. So that way, when the pipe starts heating up, well, during normal operation, it will be fine. But just that little bit of time where it's not going to be the exact same temperature throughout, will it be slamming up into each other, and it will create more wear. All right. In the chat, someone said, don't metering devices work in that manner? What do you mean by that?
Before you were talking about if the, I don't know what to call it, but if the way that the pipes connected were on the inside of the pipe, isn't that what a metering device is supposed to be? Or I'm thinking of something different.
You might be thinking of a different type of fitting that it goes on the inside. All right, but we'll go into that as far as that's a different type of fitting that's used in very special circumstances. That will be, yeah, that's going to be different. All right. So when you weld here, it's called a flit weld. All right. Normally, when you do this, it's not just going to be one weld. All right. So you're going to weld here. Come on. That's going to be my bead right there. And then you usually do 2 more on top of that. All right. So you would do 1 more right here and then another one. I drew that too big. It usually goes like this. So you'd stick 1 in there, and then 1 here, and then 1 here. All right, 3 passes or so, depending on how big it is. It usually gives a stronger weld if you do it that way. All right. Now, another type of pipe connection is threaded. All right. When you buy piping, you could buy piping as a threaded piece. There's going to be, when you go out on a ship, there's going to be containers, whole Venmars full of pipe connectors. All right, all threaded, all different sizes. Usually goes up to about 6 inches or so. So maybe if you're lucky, you get the 12. All right, it's all pre-threaded for you. You buy it that way. Usually you use it in any sort of like, use it in air systems a lot. So if you're going to be putting in like piping to go from an air compressor to an air tank, you use threaded, stuff like that. All right. So you use on pipe thread is NPT. All right. It's not the same as if it was on a machine, threads or nuts and bolts. All right. Those are in threads per inch or TPI. All right. That's a machine thread. NPT is for pipes. All right. If you notice, it actually is going to be on a slight taper. All right. You can see that line is tapered there. All right. And external threads here are going to be cut with what's called a die, D-I-E. All right. And you can see the die over here. It uses internal threads to cut external threads. All right. You've probably seen these die sets before if you wandered into the machine shop at some point. All right. They tend to be ratcheting. So that way you can constantly ratchet and you're not going to have to spin this round. All right. And then you have something called a tap. And this is going to use external threads to cut internal threads of the pipe. All right. And if we look at both of these pieces of tools, you see how there's this space right here and the space over here where it doesn't seem like there's any threads on it. Was that a mistake or what's up with that? What's going on?
It's made so that when you cut the metal, it will, the grind parts will go into those slots.
Exactly. We're removing material here, right? When we're cutting threads, we're just not magically making, you know, threads appear without actual removing material. All right. So exactly where all of those clippings go, and they go into that space, it allows you to make a cleaner thread. All right. There's an entire way to create threads. All right. You'll learn it in machine shop, but for right now, just know you have taps and dies. They cut threads. All right. And that you have a tap is used to create internal threads and a die is for external threads. All right. Now we have flange. All right. Flanges may be threaded on or welded on or cast. They could be really quite literally anything. All right. So this is a threaded version where the pipe goes into it. This one's flanged on, so you could see that the pipe continues over this way and the flange goes right on top of it. All right, so it slides over it. This one is a screw and this is a welded one right here. So it's welded on both sides to seal. All right, not only do we not want fluid to go back this way, but we don't want fluid to go this way as well. All right, And then this one is a welded neck flange. All right, so the flange continues out to the pipe, and then it has a V weld. So we can use gaskets to seal between them. All right, rubber, paper, flexible graphite, synthetics. All right, if you see this right here, that means low pressure. All right, so this is for low pressure applications. Now, that gasket material goes in between, and then you use what is called bolts. You could use studs, you could use anything like that. All right, more than likely, you'll probably have some threaded rod with nuts on either side. Sometimes you'll have bolts and nuts. All right, it all depends on the ship, what application was used, how old the ship is. All right, so going through from there, we have high pressure. Now, notice the big difference here. All right, look at the gasket, the area it takes up. All right, it's a flat surface on the low pressure. On the high pressure, what you have, and you can see it right beforehand, you see that center ring? That's a little raised. All right, if you were to look on it from the side right here, you can see the rest of the flange is a little bit farther back, and then it has a little bit of a raised material right there. All right, that is where the seal is being created. Obviously, we have a gasket, but you can tell that there is way more room in between here because that seal is happening between that little piece of metal and our gasket here. All right, and then here's the two different types of gasket material you can use for a high pressure application. These utilize studs. All right, again, you can use studs on low pressure. All right, and you would have to probably use a type of bolt, a higher grade bolt, but more than likely you'll just see studs. All right. Now look here, there's some important information right here. We have some random numbers. We have 1, 2, 3, 4, 5, 6, 7, 8. What is up with that?
That's the order you put the studs in.
That's
Work
the order.
pattern.
Is star pattern. All right. Not only is this the order you put it in, but this is the order that you tighten them down. That is your torquing sequence, your tightening sequence. All right. You don't always have to start at the top. If you want to start at number 8, start at number 8, but then number 8 becomes number 1. Then this is 2. And then we go to 3 over here, 4 over here. All right. So wherever you start, you have to follow this sequence. All right. Otherwise known as a star pattern. Okay. So doing this, why do we want to do that? Why do we want to tighten it down in this sequence?
To apply the pressure even.
Apply the pressure evenly. If you went and you tightened number 2 all the way down and then did number 7, then did number 5, all right, you would end up with a piece of material that would go like this. Right, the 2 flanges would be butted up like that, and then the top would be wide open. All right, you want this thing to be crushed evenly. It's a piece of gasket. All right. Now, one last piece of tidbit of information: paper. For you mates out there, if you ever get the question from your engineer asking for chart paper, this is why. Chart paper makes excellent gasket material. All right, it works fantastically well. It has like some sort of fibers in there. Whether with the paper, there's some string material, it holds together perfectly. It's just thick enough to be used as a gasket. So low pressure application, guys, chart paper. It works great. Don't get the stuff that they just bought, they'll kill you. But get any sort of their old stuff, works great. It also works great for wrapping paper if you have to make a present for somebody. All right. Oh, and I guess you could navigate with them too. So going from there, we have tube installations. Tube installations are never straight runs. Their deliberate bends allow for a reduction in length, which can occur as the tube is pressurized. What else will cause these to be incorrect? What are we training to do? We were training to work on land, or are we training to work on ships? Everybody's
I-
answering this.
Ships.
What do ships do?
They roll.
They roll, they move, right? When a ship gets hit with a wave, does the entire ship, if you have a ship that's getting hit with a wave all the way in the front, is the entire ship going to react the exact same way? The entire length at that instant?
No.
It's going to twist and contort, right? The whole thing. Granted, we try and reduce that, but the whole thing moves. Okay? When you get on a sea term and you look down Shaft Alley, you can actually see the entire place twisting and contorting in different directions when you get into high seas. All right? So any sort of straight run, just for that matter of fact, with that twisting, that would break any of these connections, right? So we give room not only for that, but the bending and twisting, just a little bit of extra material. All right. Also, when the tube pressurizes, you could be sitting in port and these will break just because you pressurize the system. All right. So always think about what's going on, all of the forces that are happening. All right. It's not just what's happening inside the system, but outside forces as well. All right. This could be attached to a bulkhead, not just an entire piece of equipment. All right. With another piece of tubing on the other side continuing out. So it could be rigidly connected. All right. So tube connections, we have a brazed / sweated. All right. So brazing alloy basically is a slot and fitting, and flux is applied to the tube in the clearance area. All right. So we have flux material, we have brazing material. This piece over here is our fitting. All right. The tube is heated and expands. The flux is forced out of the clearance area, and the brass alloy contacts the tube. The fitting is heated and the clearance area opens. The flux and alloy will flow out. Now, looking at all of that, all right, this is brazing. Why do we utilize flux? Is there anybody in here who does any sort of plumbing or any sort of soldering? It's the same idea.
Is it to make sure that the contacts are all the contacts are filled? Like there's like little divots and stuff in both pieces.
So yes, with that idea, all right. So what flux does, and flux is used in both soldering of electronics. I'm surprised no one here has done that. And also with soldering or sweating any sort of copper pipes together or tube connections. All right, so flux is applied. And basically, it's designed to be melted away. All right, it has a boiling point that's lower than the brazing material or the solder material. All right, when heat is applied to it. And it flows, so it melts because it's a semi-solid. It melts and then it flows into all the crevices. So if you're trying to wire up and solder two things that are all of those wires, it's not solid strand wire, all right? It's all those little tiny wires. You dip both those sides in flux and then you twist them together, all right? The way to ensure that the solder material gets deep into all those crevices and make a really solid electrical connection is the flux, because it will flow. It will move. Once it's heated, it will become that liquid and then it will boil off. But that liquid point is what we're searching for. All right. So as we apply the solder to it, the flux is flowing Well, the solder wants to search for that heat, all right? And it will follow the flux and it will get into all those nooks and crannies, all right? And make a really good seal or a really good electrical connection. That's the job of the flux, all right? Now, this brazing material is the actual solder. It's the weld. It's the actual material that will make that strong connection. All right. So no one really does any brazing anymore. Not that I've ever seen it. A lot of it is basically sweating of copper pipes. A lot of tube connections are an actual physical connector. All right, a fitting. So just know that it exists, but you're pretty much, it's the same thought that applies to any sort of soldering. All right. So instead of having the brazing material a part of the fitting, you would add a rod of whatever material, that solder that you're going to be utilizing. All right. And that will follow the flux into all of these crevices. All right. Now, another version, flare fittings. All right. You need a flaring tool to do this. All right. Tubes won't come flared. They come in straight pipe. All right. And what you have is, it's basically a tool that's a piece of metal with a V formed into it. All right. That's this piece right here. This tool is a clamp with another V in it. You put the piece of pipe into it, and as you apply pressure downwards, it will form out the tube so that it's flared. All right. These are used, but I don't like them. Not a lot of people like these. All right. They work well for a while, but depending on the material, they will eventually break. And they break a lot faster than other versions. Why is that? Why is that? Because of what we're doing to the flared pipe.
Well, you're warping it, so it like loses the integrity that it originally had.
So we're warping it. All right. So we're moving it. We're expanding the pipe. The pipe was already the tube, let's say, is 3/4 of an inch. This flare might go all the way out to an inch. Right? And we're not adding any material. We're flaring it out. We're pushing the material, making it thinner. All right. And the only thing that is sealing on here is basically these two things. We have the nut and the body connector. So it's utilizing the material to be the sealant. All right. These threads, as it pushes this force downwards, it makes a seal here and here. All right. These can become weak. They can break easier. All right. And that's because we're not adding material. We're using the material that we have here. Again, they'll work for a while, but they will fail faster than anything else. All right. And now, just to keep you aware, this is different from a flared piece of piping that you would use. All right. If you have ever done any plumbing in your house, you'll recognize that they use a lot of flare fittings on any sort of piping that's in underneath your toilet. If it's going the connector to the water shutoff underneath your sink, it utilizes these. All right, they're great at sealing when you don't use a flaring tool, when you don't actually use the material itself, the piping itself, the tube itself to create the seal. All right, so that's two different categories we have to think about. All right, when you're using a flaring tool, that's when it will fail. If it's a physical fitting that's designed to do it, that was processed, it'll be fine. Okay. All right. Now, let's talk about fittings. We know how to connect two pieces of pipe together, but we can also utilize different fittings to do it. All right. So it's not just going to be two pipes put up together. All right. So we have a cap. This stops the flow of whatever fluid is in here. All right. So it utilizes internal threads to screw onto external threads of the pipe. All right. And then we have a plug. A plug utilizes external threads to screw into the internal threads of the pipe. If we want to connect equally sized pipe sections, these are called nipples. All right. Now, we're going to go into depth on these because they can come into any sort of size and section. All right. But they utilize both external threads to screw into two sides internal threads. And then we have a coupling, and a coupling uses internal threads to screw onto the external threads of both pipes. Now, we have something called a union. All right. This utilizes internal threads on both sides. But here's the big thing about a union. It comes in three pieces. All right. If you're in a spot and you try and turn this way, all right, you're turning the pipe that way to screw on the pipe onto this direction. What happens on this side? What happens to this pipe over here?
It pulls it inward.
It's going to move the entire pipe inward, right? Well, what else happens? That only assumes that this pipe over here, it's called pipe number 1, is free moving, right? If this was welded to a wall over here, welded to a bulkhead, what would happen?
It's going to unscrew from one and screw onto the other.
It's going to unscrew from one and it will screw on to number 2. All right. So that's where unions come in. So it's 3-piece. So one of them will screw onto here. All right. The other side will screw onto the other piece of pipe. All right. And then the third piece will join those pieces together. All right. So that gets screwed in and it will screw those two pieces together and it will create a seal that way. All right. This is a full metal to metal contact here. So this is for a run of piping that can be opened without removing large sections. All right. Now, if we want to, and we'll go back to a union which has better photos and everything like that. All right. So if you want to connect unequal sized piping sections, this is called bushing. All right. So it has external threads that will screw into internal threads of the pipe. And then it has internal threads to screw on to the external threads of another pipe. All right. So this is for unequal. All right. Now, we go the other way. This is called a bell reducer. It doesn't have a picture. So a bell reducer, it looks like a bell. All right. It utilizes internal threads on both sides. If you want to connect multiple pipe sections, we have a T. So this is for a 3-way. All right. There's your 3 different directions. We have a reducing T. All right. So one side One side is a size smaller. We have a side outlet T. All right, so this one has 4 different directions. All right, so there's 1, 2, 3, and then 4 right there. We have a cross, and we have a Y branch or a Y bend. You'll see these a lot in fire equipment. So when you're walking around the ship, you can see these on every single piece of fire equipment. Right? One end is connected to the hose, one end is just open. And then we have a side outlet elbow. So we have 1, 2, and then this is our 3rd outlet. All right. Now, if you want to change the flow, all right, change its direction, we have an elbow. We have what's called a street elbow. All right, and these elbows can come in 45, 30, 90, reducing elbow, reducing street elbow, and then they have a reducing side outlet elbow. They can come in all the different versions that we saw earlier. All right, a street elbow. And this is what we were talking about that was earlier. A street elbow will go into and they will thread into the inside of a pipe. All right. This is specifically used in a spot where you don't have a lot of room. All right, because if you had an elbow here that you had to thread in here, you might not have the physical room to have this outside piece here. This is where a street elbow shines with it. All right. Now, the other thing a normal elbow does is it has like a curvature to it. It has a distance from here to the center line to where it actually stops threading in. A street elbow has a shorter curve to it. All right. So this distance is shorter. All right, so that's another thing that they have. It's not as much room. That's what's also good about a street elbow. They're very specific applications. All right. We have a U-bend. All right. And then we have a U-bend with a back outlet. All right, so the flow will go this way, and it'll come out there. Or it depends. This is your piping system. You can also have it go in. You might be trying to add a fluid to it. All right. And then they have everything in tubing fittings as well. All right. So like I said, I have different things here. Let's take a quick look. So this is Grainger's website. All right. Now you can see I've gotten a couple things clicked off here. I have 1-inch pipe and it's a length of 3 inches here. All right. That way you can see that here, look, schedule 40 pipe. All right. Then it goes to schedule 80. The nominal pipe size hasn't changed. It's still a 1-inch pipe. It's still 3 inches long. 1-inch pipe, 3 inches long, but we have a different wall thickness because it's a schedule 40 or schedule 80. All right. So out there. All right. This is a schedule 80 pipe nipple right here. All right. That's what I want. Schedule 80 threaded on both ends. And you can see how many different sizes they come in. 3/8, 1/2, 3/4, 1 all schedule 80, but the outside inches. All right. Going from there, these are all fittings. All right, these are all the different nipple sizes. All right, you can see that each one is different. If you're lucky, you'll get one of these on ship. All right, where they have a hexagon where you can actually put a wrench on there. Most of the time, it will look like this. All right. Oh, I froze. Damn it. There we go. Is that working? All right, cool. So most of the time it will look like this with just threaded in two different opposite directions. And getting a wrench on there is super fun, I can assure you. Don't damage the threads. I guarantee it will be the last one you have. All right. This is also considered a nipple right here. All right. Like I said, these things will come into about 6 inches in length before they actually start being considered piping. All right. They're still a fitting at that point. Now, here's unions. All right. So each one of them, like I said, 3 different pieces. It allows you to break 2 different pieces of pipe without having to remove whole sections. All right. So if we do this and we do cut in half, you can actually see, where did it go? There we go. This one has a gasket in it, but we'll look at that. Pop that one open. All right, that's as big as we can get it. So you can see it's got 3 different pieces of material. This one is obviously using a O-ring. All right, but most of the time you will not see it with an O-ring. It will have a flange to it where it will physically make its contact. All right, you can see here the 3 different pieces. This is one piece here, this is the second piece, and then the collar on the outside is the third. Let's see if they actually have. Nope. All right, here's a coupling. All right, they come in different shapes and sizes like I've been stating. Here's all the different plugs you can have. All right. And then all the different caps. And then finally, let's get a bell reducer up there. And this is a bell reducer. All right, you can see the internal threads on both sides. All right. Now, question in the chat is difference between a return bend with a back outlet and a Y bend. So return bend with a back outlet and a Y bend or a Y. All right. Basically comes down to the direction of where you want the fluid to go to. All right. You may not want to come out on those direct angles. All right. You may want to come out straight. All right. So that's the big difference on those things. Is remember, it's not just because this piping can go and move. You may only have that specific room to do that U-bend. All right. And you wouldn't utilize a Y-bend with that harsh 45-degree angle into it to move fluid. It would cause turbulence and everything else like that inside. All right. Any other questions? Nothing?
A random one.
Okay.
When I worked, they used the pigtail ones, and I was wondering what's the use of it for.
They use the pigtail ones. For what?
I'm not really sure. That's the problem.
You know what I've never heard of that. It's a fitting?
Yeah, it's like a loop. It's weird.
Let me see. Oh, pigtail. Where did you work?
Facilities department in a hospital.
The only thing I can see with this being utilized is, I'll pull up a picture so everyone can see. Everybody see? That's what you had, right?
Yes.
Okay. So the only thing I can see with that is room for expansion. All right. So on like steam, stuff like that. All right.
It uses steam boiler, so
Yeah. That's the only thing I can think of is that just needs room for expansion on it, where it can expand both directions on the piping. All right. Where the idea is that, give me a wire that's long enough. There we go. So the idea is that, oh boy, that's going to be fun to see is black on black. All right. The idea is that you can move it in both directions and it can still kind of hold its form linearly. All right. That's the whole idea with it. That's what I can see from it.
okay. Thank you.
Any other questions? Last minute questions before we begin the quiz? All right. So the quiz will start in 3 minutes. All right. I have the timer set for that. Now, with it, camera's got to be on. All right. If you're not in the Zoom call, you can't take the quiz. I'll be able to see that, look for it. If you're not in the Zoom call right now, you're not hearing this warning. So great job to you all. Now, the other thing, no communication, no phones. It's not open notes. All right. We have another quiz going to be on Wednesday. All right. So the only day I'm seeing you guys next week is Wednesday. All right. And then we are going to be in person come the 25th. So this is going to go real quick. All right. So on Wednesday, we will talk about what is needed for lab. All right. Because lab will start the 25th. All right. What you need to do if you're in JStart, talk to what's happening with your lead instructors. All right. And we'll go through with all of those questions then. All right. As soon as you're done, you can just leave. If you need extra time, you stay around. All right. And you're all good from that. And the quiz will begin shortly. In the quiz folder, by the way, it will show up at 11.
Professor?
Yep.
Unfortunately, my computer doesn't really have a camera at the moment.
Oh, then you're fine.
Okay.
If you don't see it at 11, try refreshing the page. If you have any questions, do that little reaction thing. When you're finished with the quiz, you can just leave. You're good. All right. I'll see you on Wednesday. And then grades will be shown at 11:30.
Mr. Calvin,
What's going on?
for my first question, it's referencing a picture, but there's no picture.
Yeah, I have the same issue.
Whoops. Sorry, guys. I got my COVID vaccine yesterday, and I was not doing great when I put this together. Give me 1 second. It'll be in there.
I said don't answer the one with the picture.
Yeah, there should be 2 with the picture. Let me
So just leave it blank.
and refreshing your page wouldn't fix it. Perfect. All right, so let me pull it up then for you guys. Do it this way. So the valve I am showing on share screen, this is for question. In the picture shown below, the pressure being regulated is the, all right? So in the picture shown, the pressure being regulated is what? Everybody find that question? All right, this one. This is valve 2. This is for, in the picture shown, the valve is maintaining what type of pressure? In the picture shown, the valve is maintaining what type of pressure?
Mr. Calloway, can you show the picture again?
Which one? Number 1 or number 2?
Number 1.
Okay.
Mr. Callan, can you show picture number 2, please?
Yep. That is not, that's the same picture. Give me a second. There's valve number 2. Valve number 2 again is in the picture shown below. The valve is maintaining what type of pressure?
My picture didn't change.
Same here. It looks like the same valve.
Same picture.
Yeah.
Let's see.
But what's the same picture?
All right, just close both of them out. There you go.
Is there a big difference between the pictures, or it looks the same?
Why is it the same photo? That's a problem. That's not right. All right. What do we need to see? Valve number 1 again?
Valve number 2.
Valve number 2. All right.
Is the picture for both questions supposed to be the same one? Because that's what I'm seeing.
Yeah. It is the same photo.
Have a nice day, Professor.
Take care.
So this is the correct photo for number 2.
Yes, it is.
Have a good day, Professor.
Have a good day, Professor.
We're good to go when we're done. All right, cool. Have a good one.
Sir, I ran out of time because of the picture thing.
Let's see. All right. So why don't you go back into it and go again with it? All right.
All right.
That was my mistake. So one-time deal.
Okay.
All good now?
Yep. Thank you.
No problem. Have a good day.
See you.